Identifying improper integrals out of the ones listed here is what we're interested in, and we want to state whether they're converging or not. The first one, integral from 0 to pi over 2 tangent x dx, is graphically illustrated here, x-axis 0 to pi over 2, and integral is saying under the tangent curve, what is this area? Tangent at 0 is 0, but tangent of pi over 2 goes to infinity is not defined. So obviously, because of that, this integral is improper, is not ordinary. But the integral computation is easy in the sense that we would do 0 to pi over 2. Instead of tangent, I'm going to write sine of x over cosine of x dx. And then sine dx can be rewritten in the form of negative d cosine over cosine. And this is nothing but minus ln absolute value of cosine x from 0 to pi over 2. Now, cosine 0 is okay, is 1, and then ln of 1 is 0. The problem is with the cosine of pi over 2, which did use 0, but then ln of 0 is undefined. So therefore, this function is undefined for the upper limit. So this integral is improper, at the same time is diverging, not converging, and it's sort of indicating that the area under this curve, which is the result of this integral, is not finite. The second integral, if we are not careful that there is a discontinuity in the range of integration from 0 to 3, because at some point x crosses 2, and exactly when x hit 2, denominator becomes 0, this function at x equal 2 is not defined. So this integral is improper as well, and we have to break it down if we want to compute into two segments, 0 to 2, integral from 0 to 2, 1 over x minus 2 cubed dx, and the other one is integral from 2 to 3 dx over x minus 2 cubed. Of course, the computation of this integral is not difficult in the sense of knowing the formula for it. So for the first one, of course, you would say negative 1 over 2 x minus 2 squared, and from 0 to 2. And for the second one, you would say the same thing, 1 over 2 x minus 2 squared, and from 2 to 3. But the problem for both of them is when we are dealing with 2, for the first one here, we are approaching 2 from the lower value, so it's 2 negative when we have to substitute for x equal to 2, and that would result in denominator becomes 0, and therefore the function is not defined. The same thing for the second component here. We are approaching 2 from the upper values, which means 2 plus. Nonetheless, we substitute for x equal to 2, and then denominator becomes 0 as well. This is undefined as well. So it's an improper integral, and it is not converging. Okay, for the third one, this one is actually proper ordinary integral, and this is graphically highlighted in this diagram that you can see. So x going on x-axis from negative 2 to 2, those are the limits of integration, and absolute value of x cubed is this curve, and effectively the integral is computing the area under the curve, limiting between negative 2 to 2 for x. Of course, we expect this to be a converging integral because we are talking about a finite integration. And computation is straightforward. We know that it's a symmetric function around the y-axis, so we can just simply rewrite as 2 times integral from 0 to 2 x cubed, because x in this range is positive, we can get rid of absolute value, and the rest of it is just straightforward. 2 over 4 x to the 4, and then 0 to 2, which translate to 1 over 2, and 2 to the 4 minus 0 to the 4, which just becomes 8. So this one is converging. For the ln, 0 to 2 ln x dx, I have visualized it here. You can see x-axis going from 0 to 2, the integration range, and the function is ln of x, which at x equal to 1, ln of x is 0 as expected. At ln as x equal to 2, it's ln 2 that is highlighted here on y-axis. And of course, when x becomes a value between 0 to 1, ln x returns a negative value, and as x is approaching 0 from positive values, you can see ln of x quickly decreases and goes to negative infinity. At ln 0, we don't have a definition of ln x. So For that reason, this integral is improper as well, and computation of the integral, one of the fastest way to deal with that is we can think of ln x as u and a function u, and then x is just our v, and we're going to use integration by parts. So I can rewrite this as x ln x uv from 0 to 2 minus integral d du. So integral 0 to 2, this time x d ln x. Okay, let's keep this for a second. So what I can do is I have x ln x 0 to 2, and then for the other one, d ln x is 1 over x. That would cancel out with this x, so it becomes integral 0 to 2 dx, which will return negative x from 0 to 2. I mean, you can effectively rewrite it this way if you want. X ln x minus 1 from 0 to 2. Now the problem is the 0 lower limit, because we have to then deal with this situation that the upper one, 2 ln 2 minus 1, is of course no problem with that, but the lower one you have to say minus limit when x goes to 0 plus, and then you would say x ln x minus 1. And here we have an issue because we have to substitute x, we have to substitute for x the value 0, and ln 0 is not defined. So for that reason, this integral is undefined. Basically, it means it's not converging, and it's an improper integral that is not converging, indicating that the area under ln x, this area, will be an infinite value, is not converging, is not finite. All right, so for the last one here, what we have, again, for the reason that at the lower limit and upper limit of integration, the denominator becomes 0, and therefore 1 over square root of 1 minus x squared is undefined, so the function of integration is not defined, and therefore it means this is improper integral. To compute it, to see whether it's converging or not, the fastest way just to it's well known that integral of 1 over rad 1 minus x squared is just arcsine, but let me just show you quickly. If I make a change of variable, say like this, imagine I make a change of variable x equal to, say, maybe the easiest one would be sine of x. So let's say, let me just remove this, not x equal, sine of u, okay. So let's say I make a change of variable x equal to sine of u. I can do that because my x in this integration moves from negative 1 to 1. That's exactly in the range of function sine of u. So that translates to my integral become negative pi over 2. Sine of pi over 2 become negative 1 to pi over 2. Sine of pi over 2 becomes 1. Dx become d sine of u, which means cosine of u du. And in denominator, I have rad 1 minus sinus squared, but rad 1 minus sinus squared becomes rad cosinus squared, and as a result, what I have is just effectively knowing that in this range cosine, in this range that u is, so let me put it this way. We have absolute value of cosine u, but the thing is, when u goes from negative pi over 2 to pi over 2, the cosine is a non-negative value. So therefore, I can just get rid of absolute value here, and that becomes cosine of u over cosine of u, which therefore give me this integration. Negative pi over 2 to pi over 2, and then I have du, and as a result, I just have u from negative pi over 2 to pi over 2, and for this reason, what I have is this situation. U can be replaced with arc sine of x. Okay, so arc sine of x. And of course, the range would be from negative 1 to 1. Okay, So what we have is effectively just saying this becomes pi as expected. So this one is an improper integral, but it is a converging one. Hope this is helpful.